Everyone. I'm Dr. Ajayshankar Jagadeesh, Research Fellow in the Department of Civil and Environmental Engineering at the National University of Singapore. The topic of my presentation is the skid resistance evaluation of pervious pavement mixtures using XRCT-based modeling. The major motivation of my work is to prevent the road accidents, in particular related to wet weather accidents. It has been reported by World Health Organization that nearly 1.35 million road accidents are reported each year. Among that, nearly 25% of the crashes are wet weather related. We as a pavement engineers are also responsible for these accidents. This epidemic is predicted to increase due to the climate change conditions. Pervious pavements play a significant role in meeting the next generation requirements to provide safety, sustainability, and resilience to climate change effects. Porous pavements are widely used nowadays because of its increased permeability, skid resistance, and acoustic absorption coefficients, resulting in reduced wet weather accidents and tire to road noise. It has been reported by the past studies that nearly 80% of the wet weather accidents have been reduced and tire to road noise has reduced by 3 to 5 decibel. Increased use of pervious pavements as the functional performance layers necessitates the understanding of pore network properties and their relationships to permeability and skid resistance. X-ray computer tomography has been widely used in the medical analysis since 1970s. In recent years, significant efforts have been made in analyzing various types of infrastructure materials using XRCT scanning and digital image processing. The use of XRCT in the field of pavement engineering started in the late 1990s, and this enables the accurate measurement of pavement internal structure within the voxel resolution. There are several applications of XRCT in pavement engineering. First is the clogging evaluation of pervious concrete. Second is the full-scale accelerated pavement testing. Third is the micromechanical modeling for shear modulus. Fourth is the fatigue testing. And the last one is the indirect tensile testing. Next is the literature review on skid resistance simulation modeling. At first, Kong and Ford developed the tire pavement interaction model using fluid structure interaction tools for pneumatic tires. Later, the developed model was extended to different kinds of tires and pavements, including pervious pavements. Srirangam et al. First introduced the usage of XRCT-based scanning in the field of tire pavement interaction studies. Later, the developed model was extended by Xu et al. To include the kinetic friction coefficients. Currently, pavement designers and field practitioners use small-scale friction experiments like British pendulum tester and dynamic friction tester. The major limitations in the laboratory measurement includes its low test speed, impractical contact mechanism, and unreliable results on coarse textured pavements. On the other hand, full-scale experiments using locked wheel traders cannot be carried out during the design stage for various samples. Hence, the usage of XRCT-based simulation models can be considered as a solution for this challenge. However, the current models lack the importance of thresholding algorithms. The present study combines the newly developed discharge-based thresholding algorithm and can offer a better depiction of tire pavement friction characteristics. Next is the procedure for pervious pavement skid resistance analysis using XRCT-based modeling. In this, the procedure has like 4 different steps. The first step involves the usage of laboratory British pendulum test and permeability test. Second step involves the XRCT-based scanning and digital image processing. Third and fourth step involves the usage of skid resistance simulation model. At first, the third step is for the intervention curve. The figure on the right shows an example of an intervention curve. So the area above the intervention curve is considered as a safe zone, and the area below the intervention curve is considered as an accident-prone zone. The step 4 is for the evaluation of performance curve for different rainfall intensities and sliding speeds. Next is the materials and XRCT scanning. 3 different pervious concrete samples were produced in the laboratory using siliceous aggregates of different nominal maximum aggregate sizes. Somatine Emotion 16-channel medical XRCT scanner was used in the current study to obtain the internal structure of pervious concrete samples. The most important step in digital image processing is the image segmentation. It is the process of binarization commonly used to divide the images of various grayscale intensities into 2 different phases. It can be classified into global and local thresholding. Even the global thresholding can be divided into multiple categories like histogram, clustering, entropy, and volumetric methods. Figure on the right shows the air void segmentation results for sample P1 using various thresholding algorithms. In this, the black color represents the void phase and white represents the cement and aggregate phase. After the threshold values are obtained, we can obtain the 3-dimensional reconstructed CT scan models for various phases like cement and aggregate phase, interconnected void phase, and isolated phase. Next is the development of locked wheel skid resistance simulation model. In this, the simulation model has two different submodels. One is the tire pavement submodel, and the other one is the fluid submodel. In tire pavement submodel, the boundary condition includes like wheel load, tire inflation pressure, and more importantly, fluid structure interface for the tire tread elements. Whereas for the fluid submodel, the boundary condition includes like velocity inlet, pressure outlet, wall boundary condition, and fluid structure interface at the wall tire tread interface. The major output from our simulation model includes the fluid uplift force and the fluid drag force. So then the friction coefficient is obtained from the experimental British pendulum test. Validation of the developed model was then carried out using the past experimental studies on concrete pavements and the back calculation procedure developed by Fa and Ong for various sliding speeds and waterfront thicknesses. It can be seen that the obtained results are in the normal acceptable range of plus or minus 3.9 skin number as per the ASTM E274 locked wheel friction test. And hence the developed model can further be used to investigate the skid resistance characteristics for different PERVIOUS concrete samples. At first, the effect of thresholding algorithms on skid number was investigated. Here, the first column represents different samples, second and third column represents different thresholding algorithms, fourth column represents the waterfront thickness, and the remaining represents the simulation results. Comparing the third and fourth column, we can see that an increase in the threshold value results in the reduced waterfront thickness because of increased pore zones. And when we compare the percentage error for waterfront thickness, we can see that the error percentage can vary from 13% to up to like minus 30%. Whereas for the percentage error for uplift and drag forces can range from 8% to minus 36%. However, the percentage error for skid number is only up to the range of 0 to 2.3% because of the usage of constant friction coefficient for various thresholding algorithms. Even the commonly used volumetric thresholding algorithm exhibits an error in the range of minus 8 to 2.9% for waterfront thickness, minus 10 to 1.5% for uplift and drag force, and less than 1% for skid number prediction. Next is the determination of intervention curves. At first, the intervention point at standard speed of 64 km/h and waterfront thickness of 0.5 mm was obtained as 30 from highway agency manuals. It was then corrected to 45 for aging and seasonal effects. Then the skid number and other sliding speeds are obtained from the simulation models. Then the final step is the determination of skid resistance performance curve for various field conditions such as rainfall intensities and sliding speeds using XRCT-based simulation model. Three figures represents three different samples. In each figures, colored line represent different rainfall intensities from 50 mm/h to 300 mm/h. In our current study, we have investigated an extreme case scenario of 300 mm/h rainfall intensity as a part of climate change effects, whereas the black line represents the intervention curve. Area above this line is considered as safe, and area below this line is considered as an accident-prone zone. Out of these samples, P1 is considered as frictionally safe, P2 fails completely, and P3 can be considered safe till 100 mm/h rainfall intensity. XRCT-based simulation models help in obtaining this useful data in the design phase without the use of full-scale accelerated pavement testing. In summary, numerical simulation model for locked wheel skid resistance characteristics was developed and properly validated. Then the effect of thresholding algorithms on skid resistance characteristics was investigated. Secondly, the discharge-based thresholding algorithm was capable to find the skid resistance adequately compared to the existing global thresholding algorithms. Finally, the threshold frictional characteristics of PERVIOUS pavement mixtures are evaluated using the intervention and performance curves. Overall, the developed a holistic framework using XRCT-based scanning, digital image processing, and simulation models can be considered as a convenient tool for the selection of frictionally efficient mixtures in the design stage. Thank you.